We are back to studying the Bayesian equilibrium. Now in the last class, we looked at the idea of a Bayesian equilibrium. And then we illustrated it with the example of a first price sealed bid auction. Right, so we learned the theory of a Bayesian equilibrium, where essentially what you need is to specify the player types, player beliefs, action spaces, and so on, and then solve for a Nash equilibrium. Right? Okay. Now today we will complicate it a little bit. You see that when we studied static games of complete information, we just looked at Nash equilibrium. Then we built in dynamic games. When we built in sequential games, we started to look for, what did we start to look for? We started to look for subgame perfect Nash equilibrium. That is a subgame perfect Nash equilibrium is a Nash equilibrium that is a Nash equilibrium in every subgame. Right? We all remember that? We look for subgame perfect and we learned to solve them through backward induction. Now backward induction doesn't really work that way in the case of sequential games that involve incomplete information. Right, because when you solve for backward induction, you need to know what node you are at. Huh? But suppose you don't know where you are, then obviously you can't use backward induction. So what we are doing is, we will develop a new concept called the perfect Bayesian Nash equilibrium. Okay, in the context of sequential games. And then we will illustrate it with the example of a signaling and a screening kind, in the lemma. Is that clear? Right. So what we are really going to do today is to, in the last class, we studied a Bayesian Nash equilibrium, which was a generalization of the static Nash equilibrium idea to games with incomplete information. Right? Sure? Now, we need to do the same thing to games which involve sequential moves. Okay? Like in the games with sequential moves but perfect information, we thought of a subgame perfect Nash equilibrium. We need to develop an alternate tool to be able to think of subgame perfection in the context of a game with sequential moves, right? And this is called, that's where the idea of a subgame perfect, a perfect Bayesian Nash equilibrium comes. Okay. So let's start with an example. Okay. Start with a simple example. So think of this game. So player 1 moves first. He can either choose R, okay, in which case the game ends, player 1 gets 1, player 2 gets 3. Player 1 can also choose Ln. He can choose either L or N. If he chooses L, now it's the turn of the second player to move. Okay? When I indicate it with a line like this, it means that player 2 has not observed the move made by player 1 if he has chosen L or R, anything other than R, L or M. So player 2 knows that either L has been chosen or M has been chosen, but doesn't know which. Player 2 then has to choose. So player 2 can choose L dash or R dash. Similarly here, L dash and R dash. Okay? And then here are the payoffs at the end. 2, 1. Okay. 0, 0. Right? And then we have 0, 2. And we have 0, 1. Right? So this is what player 1 gets if player 1 plays L and player 2 plays L dash. So player 1 gets 2, player 2 gets 1. Right? So on and so forth. First, let's try to convert that into a normal form game. So what are the strategies that player 2 has? Yeah, what are the strategies that player 2 has? L dash and R dash. What are the strategies that player 1 has? R, L and M. Okay, so let's write it. So let's first write it in a normal form. Okay? L, R, M. L dash, I dash. Okay? Right? Now, if player 1 plays L and player 2 plays L dash, what are the payoffs? 2. Right? If player 1 plays R and player 2 plays L dash, what are the payoffs? 1, 3, because that's when the game ends. Right? Okay? So you write 1, 3. Okay? If player 2 plays M and player 1 plays M and player 2 plays L dash, what are the payoffs? Yeah? 0, 2. Player 1 plays L and player 2 plays R dash, what are the payoffs? 0, 0. Okay? Player 1 plays R, player 2 plays R dash, payoffs are 1, 3. Because the game ends, no? Right? See, this strategy, the players are saying what they will play. Right? Okay. If player 1 plays M and player 2 plays R dash, the payoffs are 0. Okay? Now, can you identify the Nash equilibria from this? So, can you tell me how many Nash equilibria exist here? Okay, can you identify the Nash equilibria in this game? This is what player 1 gets, this is what player 2 gets. Two, 1. Or let's write it like this, okay? Because traditionally, typically, you represent L dash payoffs here, so that's why you're finding it difficult. So let me just interchange 1, 2, 3, 1, 2, 0, 0, 0, 3, 1. Yeah? So can you identify the Nash equilibria? Now things will be easier. Is this a Nash? Is this a Nash? No? Why are we saying no?
Both of have incentive to deviate from.
What?
Incentive to deviate from this because
Who has incentive?
player
So
one
suppose
will
player
take-
1 is playing L, player 2 is playing L dash.
But if
So as long as listen to me. As long as player 1 is playing L dash, as long as player 2 is playing L dash, does player 1 have an incentive to do anything else?
no.
Right? So as long as player 2 is playing L dash, does player 1 have an incentive to do play R or M? No. Because what will happen? His payoff should decrease. As long as player 1 is playing L, does player 2 have an incentive to do anything else? Does player 1 have incentive to play R dash? No. So nobody is incented to unilaterally deviate. Both can deviate together, but that is not what the game Nash equilibria are about. A unilateral deviation, right? So is L dash a Nash equilibrium? Yeah. Yes. Is L dash a Nash equilibrium of this game? Why?
Nobody has incentive to deviate.
Unilateral.
Yeah.
Is there any other Nash equilibrium in this game? Is there any other Nash equilibrium in this game? That's important. R? Perfect. Yes. So is R dash a Nash equilibrium? This. Is this a Nash? Yeah? Because as long as player 2 is playing R dash, does player 1 have an incentive to play L or M? No. As long as player 1 is playing R, does player 2 have an incentive to play deviate from R dash? No, because the sphere remains the same. Right? Which means that there are two Nash equilibria, L dash and R dash. So what is the L dash equilibrium? The L dash equilibrium is player 1 plays L and player 2 plays L dash. Right? What is the R dash equilibrium? Player 2 says he is going to play R dash when it is his turn to move. Strategy is not actual sequential play, but a decision, right? So player 2 says that he is going to play R dash when it's turn to move. Player 1 moves R. So player 2's turn to move doesn't come at all. But he says if whenever it's my turn to move, I will play R dash. And that is a Nash equilibrium in this because nobody has an incentive to unilaterally deviate from it. Now, I want you to answer a question. I want you to tell me I am deeply uncomfortable with the equilibrium R dash. I am deeply uncomfortable with the equilibrium R dash. Why? Do you also share my discomfort with the equilibrium R dash? And if so, why? Argue. I'll give you 5 minutes to argue. That I'll go out, talk among yourself. I'll come back after 5 minutes and please give me an answer. Right? And whatever that answer is, it will be a perfectly nonsensical answer. That's perfectly fine. Right? But it should have something to do with reasoning in the game theoretic frame. Now we have had lots of lectures on reason theory. So you have to reason at least reasonably. Have you reached an answer? Think of credibility, credible threats, and think of backward induction property. Okay, that's a hint. Think of backward induction property. See, what is this equilibrium? R dash, right? The equilibrium R dash. What is Plato saying? What is Plato saying in R dash? Plato is saying I will play R dash when it is my turn to move. So whenever I have to make my move, I will move R dash. And player 1 moves R, and that's a Nash equilibrium. But now think of a situation where player 2 actually has to make a move. Okay? Player 2 actually has to make a move. Do you think player 2 will actually move R dash when it is his turn to move? Why will you do L dash? The way you should think. But player 2 doesn't know whether he is here or here. Because he doesn't know whether player 1 has moved L or M. He doesn't know whether player 1 has moved L or M, right? So how do you then reason?
In any way, if player 2 in any case chooses L dash or R dash, if player 1 chooses R, then also is getting the same payoff in the case of L dash also. But in any other cases, when player 1 chooses L or M, he's getting higher payoffs.
So
And
what
choosing L dash.
what she's saying really is we need to put some steps. So let's assume that player 2 thinks that is either at this point or this point. That is either player 1 has played either L or M. Let's assume that he thinks that player 1 has played L with probability P and has played M with probability 1 minus. These are his beliefs. These are his beliefs, right? So we impose some belief structure. Now, how does it help? Because we can immediately now see that if player 1 plays L dash, his payoff is 1 with probability P, right, and 2 with probability 1 minus P, right? So his expected payoff from playing L dash are P yeah 2 minus P, right? What are his payoffs for playing R dash? 0 with probability P, right? And 1 with probability 1 minus P, right? So, now 2 minus P is necessarily greater than 1 minus P for any value of P. So, for whatever beliefs that player 2 might have, it makes sense for player 2 to actually play L dash when it is player 2's turn to move, right? Okay? And therefore, player 1, so if for example, then player 2 is always going to move L dash when it is his turn to move, does it now make sense for player 1 to play R? Because in the R L dash equilibrium, player 1 gets 1 if he plays R. Okay? On the other hand, what would now player 1 play? If player 1 knows that player 2 will always play L dash. L. Because if you play L, you will get 2. If you play M, you will get 0. And 2 is bigger than 1. So in fact, a rational player 1 will always play L. So there is only one sensible equilibrium, L dash. Right? Okay? Now that's an equilibrium which is also subgame perfect, because in this game there is only one subgame, the entire game. Because a subgame is a game which begins at a singleton node. A subgame is a game, part of the game tree that begins at a singleton node. Right? So clearly, this does not qualify to be a subgame, because this subgame doesn't begin at a singleton node. The only subgame which begins at a singleton node is the whole game. Right? So what we have only one, we have a subgame perfect. So basically what we then say is, L dash is a subgame perfect Nash equilibrium for the whole game. So even when we actually had R dash as a Nash equilibrium, R dash somehow is not a very satisfactory Nash equilibrium. Right? Is this clear? How we solve for a Nash equilibrium in this game? It seems logical now with L dash. Okay. But you also saw that this way in which we figured out L dash required a course of sequential reasoning. Okay? Right? So let us now formalize this reasoning, the reasoning that we did, in terms of some requirements, which have to be satisfied by any. So what we have in this case is what is called a perfect Bayesian Nash equilibrium. Because we got a subgame perfect Nash equilibrium, like that we have got a subgame perfect Bayesian Nash equilibrium. Because now we have got beliefs as well. Right? So the correct belief would actually be, for player 2 will be P is equal to 1. The correct sensible belief, if you play 2, right, if you play 2, it will be sensible to argue that P is equal to 1. Because player 1 would always play L. L dash is the only Nash equilibrium, and we just argued that player 1 in fact would always play L. So player 2 will actually know, a reasonable player 2 will actually know that he is going to be at that node. Right? He is going to be at that node. So P is equal to 1. P is equal to 1 is a belief. That belief has been reached through a certain reasoning process. Right? So let's now formalize all these ingredients of the reasoning that we did, and then let's now characterize, let's formally define a Bayesian Nash equilibrium, and then let us try to think of this in terms of a signaling game. Okay? Think of it as terms of a, yeah? Right. Okay. So now let's put some requirements here. So I'll write those requirements down. So that is requirement 1. Requirement 1. Okay? At each information set, the move must have a belief. Okay? About which node in okay? Sure? So what's the information set? When it was a turn for player 2 to move, his information set consisted of L and M. That is, player 1 could have moved L or M, so he could either be at the node representing the move L by player 1 or the node representing the move M by the player 1. So the set was L and M. The first thing that we require is a belief. Okay? Is a belief. Right? In the game that we had, we represented it by P and 1 minus P. So what's a belief? At an information set which is a non-singleton set, that is, there are more than one element in that information set, like they were here, there were two elements, right? L or M. You do not know whether you were at L or you were at M. Right? A belief is nothing but a probability distribution over the nodes in the information set. Right? So this is the probability with each node.